Conduits and Romex are two distinct electrical wiring systems employed in buildings. Conduits are typically metal pipes or tubes designed to safeguard electrical wires from physical damage and environmental factors. These conduits can be constructed from materials like steel, aluminum, or even plastic, and they can be either rigid or flexible, installed either exposed or concealed within walls and ceilings. Romex, on the other hand, is a non-metallic sheathed cable, often abbreviated as NMB, that contains multiple insulated conductors enclosed within a plastic sheath. These conductors are commonly color-coded as black, white, red, and green. Romex enjoys widespread use in residential wiring due to its flexibility, cost-effectiveness, and ease of installation. In certain regions, such as Chicago, electrical metallic tubing known as EMT is a prevalent type of conduit. EMT is a lightweight, galvanized steel tube that serves as a continuous ground path for electrical circuits. However, the use of EMT has seen a decline in recent years due to the increasing popularity of Romex and other non-metallic wiring systems. When it comes to grounding model railroading control systems that operate on a 120 volts AC input, it's crucial to connect the ground terminal to the green ground wire in the power outlet. This practice ensures proper grounding, mitigating the risk of electrical shock. In situations where green wire is absent, such as when using conduit, it's acceptable to connect the ground terminal directly to the metal conduit. The conduit itself acts as a continuous ground path, providing the necessary grounding for the system. Some individuals may be unfamiliar with conduit, particularly if they reside in areas where Romex is the predominant wiring method. Wiring practices and preferences can vary significantly across different regions. When assessing the safety of a home wired with EMT, it's important to recognize that EMT is a safe and effective wiring method that complies with the National Electrical Code. While Romex may be more prevalent, EMT remains a viable option that doesn't inherently pose significant safety concerns. Conduits serve as a means of protecting and grounding electrical circuits, offering a robust alternative to Romex. While Romex enjoys greater popularity in residential wiring, EMT continues to be utilized in various areas. Grounding model railroading control systems correctly involves connecting the ground terminal to the green wire or, if a green wire is unavailable, to the metal conduit. When working with electrical systems, several key concepts and practices are essential to ensure safety and compliance. Firstly, understanding the National Electrical Code, or NEC, is paramount. The NEC provides comprehensive guidelines for electrical installations, covering aspects such as wiring methods, grounding, overcurrent protection, and equipment specifications. Familiarity with the NEC is crucial for both electricians and anyone working with electrical systems. Secondly, grounding plays a vital role in electrical safety. Grounding involves creating a low impedance path for fault currents to return to the source, which helps prevent electrical shock hazards and equipment damage. Proper grounding techniques include using grounding conductors, bonding metal enclosures, and ensuring a continuous ground path throughout the electrical system. Thirdly, overcurrent protection devices, such as circuit breakers and fuses, are designed to protect electrical circuits from excessive current flow. These devices automatically interrupt the circuit when the current exceeds a predetermined level, preventing overheating, fires, and equipment damage. Selecting the appropriate overcurrent protection device for a given circuit is crucial for safety. Fourthly, wiring methods encompass the various ways electrical conductors are installed and protected. Common wiring methods include conduit, Romex, cable trays, and direct burial cables. Each wiring method has its own advantages and limitations, and the selection depends on factors such as the environment, voltage level, and ampacity requirements. The NEC specifies the requirements for each wiring method to ensure safety and reliability. Fifthly, voltage drop refers to the decrease in voltage along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment malfunction, reduced efficiency, and overheating. It's important to calculate voltage drop in electrical circuits to ensure that it remains within acceptable limits. Factors that affect voltage drop include conductor size, length, and current. Sixthly, ampacity refers to the current carrying capacity of a conductor. The ampacity of a conductor depends on its size, insulation type, and installation conditions. The NEC provides ampacity tables that specify the maximum allowable current for various conductors under different conditions. It's crucial to select conductors with adequate ampacity to prevent overheating and insulation damage. Seventhly, bonding involves connecting metal enclosures, raceways, and equipment together to create a continuous electrical path. Bonding helps minimize voltage differences between metal parts, reducing the risk of electrical shock. Proper bonding techniques include using bonding jumpers, bonding bushings, and ensuring tight connections. Eighthly, electrical safety practices are essential to prevent electrical accidents and injuries. These practices include energizing circuits before working on them, using insulated tools, wearing personal protective equipment, and following lockout/tagout procedures. Additionally, it's important to be aware of potential hazards such as exposed wires, damaged insulation, and overloaded circuits. Ninthly, electrical testing and troubleshooting are crucial for maintaining electrical systems. Common testing procedures include voltage testing, continuity testing, and insulation resistance testing. These tests help identify faults, diagnose problems, and ensure that electrical systems are operating safely and efficiently. Tenthly, electrical codes and standards are constantly evolving to reflect advancements in technology and safety practices. Staying up to date with the latest codes and standards is essential for electrical professionals and anyone working with electrical systems. Organizations such as the National Fire Protection Association, or NFPA, and the Institute of Electrical and Electronics Engineers, YEE, develop and publish these codes and standards. The NEC is updated every 3 years to incorporate new requirements and address emerging issues. When working with electrical systems, it's essential to consult the latest edition of the NEC to ensure compliance and safety. The NEC covers a wide range of topics, including general requirements, wiring and protection, wiring methods and materials, equipment for general use, special occupancies, special equipment, and communications systems. Understanding the NEC organization and content is crucial for navigating its complex requirements. Firstly, Article 90 of the NEC provides an introduction to the code, outlining its purpose, scope, and organization. It also defines key terms and concepts used throughout the code. Secondly, Chapter 1 of the NEC covers general requirements for electrical installations, including wiring methods, grounding, overcurrent protection, and equipment specifications. Thirdly, Chapter 2 of the NEC addresses wiring and protection, including conductor sizing, overcurrent protection, device selection, and grounding and bonding requirements. Fourthly, Chapter 3 of the NEC covers wiring methods and materials, including conduit, cable, and raceway systems. It specifies the requirements for each wiring method, including installation methods, support requirements, and ampacity ratings. Fifthly, Chapter 4 of the NEC addresses equipment for general use, including luminaires, appliances, and motors. It specifies the requirements for each type of equipment, including wiring connections, grounding requirements, and overcurrent protection. Sixthly, Chapter 5 of the NEC covers special occupancies such as hazardous locations, healthcare facilities, and places of assembly. It specifies additional requirements for electrical installations in these occupancies to address the unique hazards associated with them. Seventhly, Chapter 6 of the NEC addresses special equipment such as electric signs, elevators, and swimming pools. It specifies additional requirements for electrical installations involving these types of equipment. Eighthly, Chapter 7 of the NEC covers special conditions such as emergency systems, standby power systems, and fire alarm systems. It specifies the requirements for these systems to ensure their reliability and performance. Ninthly, Chapter 8 of the NEC addresses communication systems such as telephone, data, and CATV systems. It specifies the requirements for wiring and equipment used in these systems to prevent interference and ensure signal quality. Tenthly, Annexes A through J of the NEC provide supplementary information such as examples, tables, and calculations. These annexes are not part of the enforceable requirements of the code, but they can be helpful for understanding and applying the code's provisions. When working with electrical systems, it's essential to follow safe work practices to prevent electrical accidents and injuries. Firstly, always de-energize circuits before working on them. This can be accomplished by turning off the circuit breaker or removing the fuse that supplies power to the circuit. Secondly, verify that the circuit is de-energized using a voltage tester. This will ensure that the circuit is not still energized due to a backfeed or other unexpected source of power. Thirdly, use insulated tools when working on electrical circuits. Insulated tools are designed to protect you from electrical shock in the event that the circuit is accidentally energized. Fourthly, wear personal protective equipment, or PPE, such as safety glasses, gloves, and a hard hat. PPE can help protect you from a variety of hazards, including electrical shock, arc flash, and physical injuries. Fifthly, follow lockout/tagout procedures when de-energizing circuits. Lockout/tagout procedures involve placing a lock and tag on the circuit breaker or disconnect switch to prevent it from being accidentally turned on. Sixthly, be aware of potential hazards such as exposed wires, damaged insulation, and overloaded circuits. These hazards can increase the risk of electrical shock, fire, and equipment damage. Seventhly, never work on electrical equipment when you are wet or standing in water. Water is a good conductor of electricity, and working in wet conditions can significantly increase the risk of electrical shock. Eighthly, never overload electrical circuits. Overloading a circuit can cause the wires to overheat, which can lead to a fire. Ninthly, use ground fault circuit interrupters, or GFCIs, in wet locations such as bathrooms, kitchens, and outdoor areas. GFCIs are designed to protect you from electrical shock by quickly interrupting the circuit when a ground fault is detected. Tenthly, inspect electrical equipment regularly for damage. Damaged equipment can pose a safety hazard and should be repaired or replaced immediately. When grounding electrical systems, it's important to follow proper grounding techniques to ensure safety and prevent equipment damage. Firstly, use grounding conductors of the appropriate size. The size of the grounding conductor is determined by the size of the circuit conductors. Secondly, bond metal enclosures and raceways together. This will help to create a continuous electrical path for fault currents to return to the source. Thirdly, ensure that the grounding electrode system is properly installed. The grounding electrode system provides a connection to earth, which helps to stabilize the voltage of the electrical system and provide a path for fault currents to dissipate. Fourthly, use grounding bushings and bonding jumpers when connecting conduit to enclosures. Grounding bushings and bonding jumpers help to ensure a low impedance connection between the conduit and the enclosure. Fifthly, avoid creating ground loops. Ground loops can occur when there are multiple ground paths in an electrical system. Ground loops can cause noise and interference, and they can also increase the risk of electrical shock. Sixthly, use isolated ground receptacles for sensitive electronic equipment. Isolated ground receptacles have a separate grounding conductor that is isolated from the building's normal grounding system. This can help to reduce noise and interference in sensitive electronic equipment. Seventhly, test the grounding system regularly to ensure that it is functioning properly. Grounding system testing can be performed using a ground impedance tester. Eighthly, consult the NEC for specific grounding requirements. The NEC provides detailed requirements for grounding electrical systems, and it's important to follow these requirements to ensure safety and compliance. Ninthly, understand the difference between equipment grounding and system grounding. Equipment grounding involves grounding the metal parts of electrical equipment to provide a path for fault currents to return to the source. System grounding involves grounding the neutral conductor of the electrical system to provide a reference point for voltage. Tenthly, recognize the importance of grounding in preventing electrical shock hazards. Grounding provides a low impedance path for fault currents to return to the source, which helps to prevent electrical shock in the event of a ground fault. In addition to the concepts discussed earlier, understanding electrical formulas is essential for analyzing and designing electrical circuits. Firstly, Ohm's law describes the relationship between voltage, current, and resistance in an electrical circuit. Ohm's law states that voltage equals current times resistance, or volts equals amps times ohms. This formula can be used to calculate any of the three variables if the other two are known. Secondly, the power formula describes the relationship between power, voltage, and current in an electrical circuit. The power formula states that power equals voltage times current, or watts equals volts times amps. This formula can be used to calculate the power dissipated by a circuit element, such as a resistor or a lamp. Thirdly, the voltage drop formula describes the decrease in voltage along a conductor due to its impedance and the current flowing through it. The voltage drop formula states that voltage drop equals current times impedance, or volts equals amps times ohms. This formula can be used to calculate the voltage drop in a circuit to ensure that it remains within acceptable limits. Fourthly, the parallel resistance formula describes the total resistance of multiple resistors connected in parallel. The parallel resistance formula states that the reciprocal of the total resistance equals the sum of the reciprocals of the individual resistances. This formula can be used to calculate the total resistance of a parallel circuit. Fifthly, the series resistance formula describes the total resistance of multiple resistors connected in series. The series resistance formula states that the total resistance equals the sum of the individual resistances. This formula can be used to calculate the total resistance of a series circuit. Sixthly, the transformer turns ratio formula describes the relationship between the number of turns in the primary and secondary windings of a transformer and the voltage and current ratios. The transformer turns ratio formula states that the voltage ratio equals the turns ratio and the current ratio equals the inverse of the turns ratio. This formula can be used to calculate the voltage and current in the secondary winding of a transformer if the voltage and current in the primary winding are known. Seventhly, the capacitor reactance formula describes the opposition to alternating current flow offered by a capacitor. The capacitor reactance formula states that capacitor reactance equals 1 divided by 2 times pi times frequency times capacitance. This formula can be used to calculate the reactance of a capacitor at a given frequency. Eighthly, the inductor reactance formula describes the opposition to alternating current flow offered by an inductor. The inductor reactance formula states that inductor reactance equals 2 times pi times frequency times inductance. This formula can be used to calculate the reactance of an inductor at a given frequency. Ninthly, the impedance formula describes the total opposition to alternating current flow offered by a circuit containing resistance, capacitance, and inductance. The impedance formula states that impedance equals the square root of the sum of the squares of the resistance and the reactance. This formula can be used to calculate the impedance of a circuit at a given frequency. Tenthly, the power factor formula describes the relationship between the real power and the apparent power in an alternating current circuit. The power factor formula states that power factor equals real power divided by apparent power. This formula can be used to calculate the power factor of a circuit, which is a measure of how efficiently the circuit is using power.